In this video, we'll discuss another operation that is very important in the heap, and that operation is the build heap operation when we already have these n elements upfront with us. Usually, this is the scenario that we encounter whenever we try to use heap, because we have an application that's generating data. So data, maybe the data is stored inside a linked list, or maybe it's stored in a database, and we read a subset of that dataset, and we want to treat that dataset as a heap for some purpose, for some priority processing purpose. So in that case, we have n elements upfront. But if we want to create a heap out of those n elements, there are two ways. The first way is that we just pick one element at a time and use the insert operation to insert it into the heap. So, for example, if we have elements in a linked list, what we do is that we pick the first element, we insert it in the heap, it becomes the root node. Then we pick the second element, insert in the heap, so it would insert at this level and then percolate up if the value is smaller. Then we add another value, that is the right, and then it percolate it upwards. Then we add the third value, it's added here, and it goes upward, maybe the two steps up towards the root. So for every insert, what we need to do is that we need to insert it at the end and then percolate it upwards. That's the insert operation, if we call this insert operation for the values one after the other. Um, that's one way to build a heap from n elements. The second idea is an improvement of this knife idea. It says that instead of adding elements one by one, just say that all these elements, they are part of an array. So if I just keep the order of these data elements and add them into an array, that's just the operation of order n, right? Adding n elements into an array without the mention of any order or sequence. We just pick first element, store it at index number one. Okay, we skip this index number 0 for a tree-based implementation. Then we pick second element, insert it at index number 2, then the third element at index number 3, and so on. So this is inserting n elements in an array, and it takes n steps. Okay, so if we have these n elements, we definitely have an almost complete binary tree with us. Now, but this tree is almost complete, but this does not follow the heap order property. So what we can do to maintain the heap order property is a very interesting idea. Is that what we do is that these leaves are definitely following the heap order property, because they do not have any child, and they have a value that is not to be compared with anyone. So what we do is that we pick the internal nodes of the tree, that are the nodes with either one or two children. So we pick the internal nodes, and we try to adjust them while comparing them with their children. So the good idea would be that we pick the last internal node first, and then we move towards the left of this level, and then we move similarly towards the upper level and start from the right of the level towards the left. So what we would do is essentially is that if I just grow this tree a little bigger, what we essentially want to do is that we start from the second last level and start from its right towards its left. So we would first process this node, then process the second last, then the third last, then the fourth last. Then we move in on the third last level. That was the second last level. This is the third last level. So we move on the third last level and start it again from right to left. So we will process this value, then we will process this value, and eventually the last value to be processed would be the root value. And what we do at every node is that we just percolate it downwards. Remember, we just use that percolate down process in the delete operation. So what it does is that it compares the value with its children and pick the smaller child and move it upwards and swap it with the parent. And the parent goes down until it reaches its desired location. So when we actually perform this percolate up operation on this entire level, we have these subtrees as what you can say sub heaps. These four are the small heaps. We want to combine them, and then when we call the percolate up on this node, it goes down on any branch, and this part of the tree again is a sub heap. But then we um, follow the same procedure on this second last node and then the root node, so the entire tree is converted into a heap. So this is the idea. So let's see how we do that. If we have all these values, we just add them into an array, and this is the structure that we have. Now this is a complete tree, but it's not following the heap order property. So we skip these leaf nodes and start from the second last level, and from on the second last level we start from the second from the rightmost value. So if I want to reach this value from this array, what we can do is that if these values are actually um, 15 values, so the index would be, the last index is index number from 0, which we just skip for the 15 values, the last index would be index number 15. This is index 1, then 2, 3, 4, so on. This is 15. I just divide this value by 2. I reach the value that is 15 by 2 is index number 7. So I start with index number 7. And to reach this last internal node is just a division operation. So I start with this node and I call the percolate down or heapify down operation on this node. And what I get is that this is a smaller value, so it doesn't move downwards. Then I check on this second node, and what I get is that 50 is smaller than 70, right? So I simply swap these two values. So after swapping these two values, 50 goes upward and 70 goes downwards. That's a swapping. Then on this particular node, 10 is the smaller value, so we do not do anything. Then on this next node 30, the smaller value is 20, so it moves up, and we move this 20 goes up in the tree. So 20 goes up in the tree here, right? 20 goes here, and now if you see this level, or these four trees are now proper heaps. Now what we need to do is that we need to check this level as well. So for the next operation we pick 40. So this 40, we compare it with the children, it's the smaller value, we do nothing. Then we move on to the further previous value, that is the value 80. When we compare it with its children, 10 is the smallest value, so we swap 10 and 80. And similarly it's compared with 60, and 60 goes up, 80 goes to the end, the bottommost level of the heap. Then the last value, that is the root value, we compare it with the children. The smaller value is 10. Then we further compare it with the children, the smaller value is 20. Then we further compare it with the children, and the smaller value is 30. So 150 moves from the root to the leaf level. And now this tree is a complete heap, right? So that's the operation, build heap for the heap, that is slightly efficient than the knife operation, where we call the insert operation n number of times. Okay, so that's the final heap. Um, There's some questions that you should ask yourself, that what's the cost of each of these operations. So first, if we talk about the percolate up or percolate down operation, what we simply want to know is that, for example, for the worst case, we call percolate up operation on this leaf. It would at the max reach up till the root level, and similarly if we call percolate down on root, it can move downwards and probably reach a leaf level. So what we essentially want to know is the height of a binary tree that is complete, and we already know that the height is order log base 2 of n. So that's the initial point, that the operation percolate up or percolate down, these are of order log base 2 of n. Okay, and now for you guys, I would leave these three operations to you, um, that you need to find the complexity of insert, delete, and build heap operation. And this, of course, this is the most complex one, but of course you can get the efficiency. We'll discuss these efficiencies in the class. So before coming to the class, you should first try to come up with the costs of these functions, and then we'll discuss the cost in the during the lecture hours.